Today's lecture is on glycogen metabolism. This is a two-part lecture. First part will be done today, and that is on the breakdown of glycogen, and the second part, which will be done later, will be on the synthesis of glycogen. So looking at the learning outcomes which would cover both of these lectures, you should be able to outline the steps leading to both glycogen synthesis and breakdown, explain how the hormones insulin, glucagon and epinephrine regulate the metabolism, indicate how the control of glycogen metabolism differs between the liver and the skeletal muscle, and to know how these differences will relate to physiological functions. Now today's lecture will cover the following areas. We will review the structure of glycogen, outline the steps in glycogen breakdown, describe the role of glycogen phosphorylase and the debranching enzyme, and compare the fate of glucose 1-phosphate in relation to other pathways, and finally discuss the regulation of glycogen breakdown. The rest of the outline shown here in red will be covered in part 2. So this glycogen, which you are familiar about, is a major form of stored carbohydrate in animals' tissues. Now, where is it stored in these tissues? It is stored in the cytoplasmic granules of the liver mainly and the skeletal muscle. If you see these diagrams, the black dots here are the glycogen granules. So it is abundant in the liver compared to the muscle, but these are the two places or the two organs which would have glycogen granules. Looking at the structure of glycogen, it is a highly branched homopolysaccharide molecule. So when you say polysaccharide, that means it is made up of many monosaccharides. When you say homopolysaccharide, it is the same monosaccharide that is involved. In this case, it is glucose. So many molecules of glucose bind together to form glycogen. And this glucose, to be more specific, is alpha D glucose, and the glucose molecules are linked by alpha 1,4 glycosidic linkages. Also, I said earlier that this is a branched homopolysaccharide. At the point of branching, the bond there is a alpha 1,6. So this diagram shows it more clearly. You will get the glucose molecules bound by alpha 1,4 linkages, and at the point of branching, you would get a alpha 1,6 link. So what are the advantages of having this structure? This glycogen molecule is able to readily remove the glucose and provide it to other pathways, which would ultimately utilize the glucose to give rise to energy. What is the function of glycogen? It is the reserve of instant energy. Now, in the liver, what happens is the stored glycogen is broken down when the need arises, and glucose is converted into glycogen when the need is arised. So what the need is the regulation or the maintenance of the blood glucose levels. So the liver will be able to regulate or maintain blood glucose levels. What happens in the skeletal muscle? Here we do not regulate the blood glucose levels. What happens in the skeletal muscle is the synthesis and breakdown of glycogen is used for the energy requirements of this muscle itself. So the main point here is that skeletal muscle does not regulate blood glucose levels. It is the liver glycogen that regulates the blood glucose levels. Let's look at the glycogenolysis or the breakdown of glycogen. The process of breakdown is glycogenolysis or lysis of glycogen. Glycogen is broken down to glucose units. To be more specific, glucose 1-phosphate units. Now, this is not a reversal of the synthetic reactions. What that means is breakdown of glycogen is not the reversal of synthesis of glycogen. The enzymes involved, the procedure itself is different. So where does this glycogenolysis happen? If we find glycogen in the liver and the skeletal muscle, it is in these two places that the glycogenolysis happens. And why does it happen in these two places? As explained before, in the liver, the main reason why we need glycogenolysis is to supply glucose to the blood. In other words, to maintain the blood glucose levels. And this glucose, which is released to the blood, is then transported to other organs, tissues and cells. In the skeletal muscle, why does glycogenolysis happen? Here it happens to meet the energy requirement of the muscle cell. So what metabolic conditions turn the glycogen breakdown pathway on and off? So as many of the regulation pathways, here also there are switches to turn something on and turn it off. Let's see what turns the glycogen breakdown on. When do we need glycogen to be broken down? When our body needs energy. In other words, in an instance that we are fasting. If we have not eaten, if there is no glucose in the blood, if we are in a fasting state, then glycogen will break down and release glucose to the blood. Similarly, if we are exercising, active exercising, at that instance your skeletal muscle needs energy and the glycogen will break down. So at these two instances, it should be on. What makes the pathway on? Allosteric activation of enzymes, hormonal activity. And what are the hormones that are involved? The two hormones, glucagon and epinephrine, are involved in the breakdown of glycogen. So what metabolic conditions will turn the glycogen pathway on and off? The second part would be what turns it off. So what would turn it off? When we have adequate glucose in our blood, we don't need to break down more glycogen. In other words, when we are in a well-fed state, when you have just eaten or when there is adequate glucose in your blood, you don't need to break down more glycogen and release more glucose. So at that point, it will be off, the pathway will be off. Or if your skeletal muscle is at rest, if you are not exercising, then your muscle doesn't need energy. At this point, the pathway will be switched off. So what makes the pathway off or what switches it off? Again, it is the inhibition or the allosteric inhibition of the enzymes and as before the hormonal activity. But the hormone here is different. It would be insulin. So insulin turns glycogen breakdown off, glucagon and epinephrine turns it on. What are the starting and ending molecules of glycogen breakdown? We start the pathway with glycogen. So it is glycogen that we need to break down. And ultimately what do we get? The end point is glucose. And what is the key enzyme in glycogenolysis? Glycogen phosphorylase. Now this reaction, glycogen converting to glucose 1-phosphate with glycogen phosphorylase, is the most important reaction in this whole pathway. So let's look at what happens, a small animation to see what really happens here. Now what I have shown here is your homopolysaccharide, just a small fraction of it. Now here you will see all your glucose molecules, alpha D glucose molecules. They are linked by alpha 1,4 linkages. These green lines are the alpha 1,4 linkages. And at the point of branching, you get the alpha 1,6 linkage. And again at the branch point, you will see the alpha 1,4 linkages. So now if you recall, the enzyme we said that is very important is glycogen phosphorylase. Let's see what glycogen phosphorylase does. So it will act on the alpha 1,4 glycosidic linkage and release a glucose 1-phosphate. So the remaining molecule is still termed glycogen, just that it is N-1. One glucose had been released. So this process will continue. Now this is the same glycogen with one glucose less. So you get the glycogen phosphorylase coming and breaking the glucose at the branch. So just like the main core, the branch also has glucose molecules which can be broken down by phosphorylase enzyme. Next, what will happen? What do you think? Do you think this glucose will continue to break down until the very end? No. There are two more enzymes that are involved here. One is called transferase. What transferase does is, it is able to shift 3 glycosyl units to the core by transferase, right? So transferase will come into play and it will cleave that alpha 1,4 linkage and it will transfer those 3 units to the core. Now we are left with just 1 glucose unit at the branch, and the link here is a alpha 1,6. So we got the enzyme alpha 1,6 glucosidase coming in, breaking the alpha 1,6 and giving rise to a free glucose at this point. So all of these, the rest of this core can be further broken down by your phosphorylase enzyme. So all of these glucose molecules will be broken down, giving rise to glucose 1-phosphate. Now let's see the same reaction which is shown in the chemical structure. So you get your glycogen molecule which has end residues or many residues of glucose bound by this alpha 1,4 linkage. Glycogen phosphorylase comes in and breaks it down to glucose 1-phosphate and N-1 of glycogen. This reaction has only one direction forward. It will only proceed to the right side, and phosphorylase is specific for that alpha 1,4 linkage. And the released sugar, if you noticed, was all phosphorylated. It was glucose 1-phosphate. So do we need further ATP to phosphorylate it for glycolysis? No, because the glucose is already phosphorylated. So you don't need to invest in ATP anymore. It will continue to go into glycolysis directly. So this phosphorylated product, this glucose 1-phosphate, cannot leave the cell. It will remain in the cell. Now, if you recall, we talked about 3 enzymes for the breakdown of glycogen: phosphorylase, transferase, and alpha 1,6 glucosidase. These 2 enzymes together are known as the debranching enzyme. So activity of these 2, they are compound together called a bifunctional polypeptide molecule, will give rise to the debranching enzyme. So what happens next? So now you got the glucose 1-phosphate, which is then translocated into the endoplasmic reticulum and converted to glucose 6-phosphate by phosphoglucomutase. And this glucose 6-phosphate is further converted to glucose, and this glucose will enter the blood. So where does this take place? It will take place, this full reaction will take place only in your liver and not in the muscle. So in the muscle, the reaction stops here, but in the liver, it goes down to glucose. Why is that? Because it is only the liver that contains the glucose 6-phosphatase. Muscle does not have this enzyme. Why? Why does the muscle not have this enzyme? That is because the liver releases glucose to the blood to be taken up by the other organs. It is the liver that regulates the blood glucose levels. I am repeating this point over and over again to stress its importance. The liver regulates the blood glucose level and not the muscle. So in the muscle, we don't need glycogen to finally convert to glucose. Muscle will retain the glucose 6-phosphate and use that for energy. And the phosphorylated glucose is not transported out of the muscle cell. Coming back to our reaction or the metabolic pathway of glycogen breakdown. How does glycogen breakdown pathway connect to other pathways? Now the glucose 6-phosphate that we got here can enter glycolysis and pentose phosphate pathway, or the liver can convert it to glucose and enter into the blood. So this is the 3 fates or the 3 fates of glucose 6-phosphate: entering glycolysis, entering pentose phosphate pathway, or being subject to breakdown to glucose and entering the blood for regulation. What are the control points for regulating the glycogen breakdown pathway? Let's look at the regulatory steps. Everything needs to be regulated. What regulates the glycogen breakdown? This is the pathway. Glycogen phosphorylase enzyme breaking down glycogen to glucose 1-phosphate. The first reaction, that is the regulatory step. So our glycogen phosphorylase is an allosteric enzyme, which means it can change between 2 states. It can be in the active state or it can be in the inactive state. So when it is in the active state, the active site is exposed. When it is not, it is in the inactive state. So now in the liver, when you are in the well-fed state, you have enough glucose in the blood, and this glucose 6-phosphate and the free glucose will inhibit glycogen phosphorylase. So if you have enough glucose, the feedback inhibition will prevent the forward reaction. So feedback inhibition of glycogen phosphorylase by glucose will prevent further breakdown of glycogen. Also, if you are in the well-fed state, you have ample ATP in the body. So this ATP will also inhibit glycogen phosphorylase. What happens in the muscle during contraction? Now, when your muscle contracts, there are two things that come in. One is calcium, one is AMP, because when your muscle is exercising in extreme conditions of anorexia, your ATP is depleted and you will have adenosine monophosphates, AMP. So this AMP and calcium, which is released during contraction, are both able to stimulate or activate glycogen phosphorylase, and this activated glycogen phosphorylase will convert glycogen. So considering the hormones, now we said glucagon and epinephrine are what stimulates glycogen breakdown. The liver is responsive to mainly glycogen and somewhat to epinephrine. However, the muscle is only responsive to epinephrine. And both of these are involved in a cascade of reactions which will activate a G protein. So G protein dependent signal transduction pathway that takes place here. So the final effect would be the activation of glycogen phosphorylase. A few hormones are enough to stimulate the release of a large amount of glucose 1-phosphate molecules. So let's see the stimulation and inhibition of glycogen diagrammatically. What you see here is the signal transduction pathway. Here you can see glucagon, which is bound to the glucagon receptor in the liver, and you will see the epinephrine in the muscle and the liver both. So in both instances, the same thing will take place. So what happens here is, once glucagon binds to the receptor, it will activate adenylyl cyclase, and this adenylyl cyclase will activate your protein kinase. It's a cyclic AMP dependent protein kinase which becomes active, and this protein kinase will activate glycogen phosphorylase kinase, and this glycogen phosphorylase kinase will activate glycogen phosphorylase. So that's why we say there's a cascade of reactions. Just one hormone that binds here will give rise to all of these reactions activating each other. And this happens in both the muscle and in the liver. In addition to this, let's see what would happen in the muscle with regard to calcium and AMP. Now in your muscle, we said the calcium, when the muscle is contracting, calcium is released from the sarcoplasmic reticulum, and this calcium can bind to the calmodulin subunit of phosphorylase kinase. So this is the inactive phosphorylase kinase. So when there is calcium, it will bind to the calmodulin unit of this phosphorylase kinase and activate it. It will activate this without the phosphorylation, right? So what it means is calcium binds to the calmodulin subunit of the phosphorylase kinase and activate it without phosphorylation. So you don't need to go through all of that. It will activate it without the phosphorylation, and you will have an active form of glycogen phosphorylase. And this active form can then activate glycogen phosphorylase, and this will give rise to the degradation of glycogen. Similarly, AMP in anorexic conditions, when your ATP is depleted, the AMP can directly go and activate glycogen phosphorylase. So you don't need any of the phosphorylations taking place. It will activate glycogen phosphorylase and convert it to active form of glycogen phosphorylase. So what are the additional regulatory molecules involved in the glycogen breakdown? So other than what we have talked so far, you have coenzymes coming in. So, this most important regulatory reaction where glycogen is converted by acting of glycogen phosphorylase on it needs pyridoxal phosphate. So, pyridoxal phosphate is a coenzyme. It is a derivative of vitamin B6 or pyridoxine. So, now finally, if we summarize what we have talked about here, the purpose of glycogenolysis is twofold. The glycogenolysis takes place in your liver and in your skeletal muscle. So, in the liver, the glycogen is mainly there for the glycogen breakdown is mainly there for the regulation of the blood glucose levels. In the skeletal muscle, the main purpose is energy for that own muscle. So, here in the liver, glycogen breaks down to glycogen 6-phosphate and finally to glucose. In the muscle, it will remain in glucose 6-phosphate. So, this is the purpose of glycogenolysis. The references used for this lecture was from the Lippincotts and the Harpers, and those two books are the recommended readings for the students, and it would be good if you all go back and look at these books after referring to this lecture. Now, this lecture was just the part 1 of glycogen metabolism. Part 2 would be done later, and part 2 will cover the synthesis of glycogen. Thank you.